Here's a quick description of homework set number 3 for ECE 111. Now the homework problems change every semester, but be kind of similar. To get to this, again go to Bison Academy, the semi-official website for the ECE department at NDSU. Under 111 takes you to the syllabus. And we're right here on week number 3 when we talk about using MATLAB to solve types of problems that you'll encounter when you take trigonometry. Now the first problem is adding points in polar form. Now in electrical engineering we use polar and rectangular form quite a bit because when dealing with sine waves you have sine and cosine. Sine and cosine would be the rectangular form. If I have a sine wave I also have the amplitude and the delay. That'd be the polar form. And you can switch back and forth between the two, so we switch between rectangular and polar form quite often. This is kind of leading up to that. The first one is add vectors in polar form. So what that says, I have amplitude at 6 at minus 93 degrees, plus 11 at 70 degrees, plus 8 at 87 degrees. Where do I wind up? Well, in MATLAB, one way to do that is as follows. So here I'm going to calculate the x and y coordinates of the first vector. The amplitude is 6. The angle is minus 93 degrees. And in MATLAB, everything's in radians, so I have to convert to radians. The second point is 11 at 70 degrees. Convert that to x and y coordinates, and so on. I didn't do the whole problem. Then, once you're in x, y coordinates, the x's add and the y's add. So if I run that in MATLAB, you get the answer. So running this, there's the first coordinate, x and y coordinate, x and y coordinate, here's the answer. So that's the first problem. Repeat for part B and part C. If I do A minus B, I wind up at a point. Where's that in polar form, the amplitude and the angle? Problem 4 looks at plotting functions in MATLAB. Now the plot function in MATLAB plots x versus y. If I'm on polar form, I have to convert that to x versus y. And to do that, the x-coordinate is r times cosine theta, y-coordinate is r times sine theta. And note that I have to use the dot times. That tells MATLAB, don't treat this like a matrix, something we'll talk about a little bit later. Treat this as 1,000 separate numbers, do each calculation separately. So put in the function of the radius as a function of angle, then run it, and what you get is the resulting plot. You're going to get a lot of circles. Trig functions are all about circles, so don't be surprised if the answer is a circle or something similar. Problem 5 and 6 is forward kinematics for a robot. Now, the way robots work is I have 3 different lengths. In this case, one's 3 meters, 2 meters, and 1 meter. I specify the angle of the first link with the length of 3. I specify the angle of the second link, length of 2, and the third link, length of 1. And the angles are relative to the previous angle. So this is the angle theta 1. This angle right here is theta 1 plus theta 2. The third angle is theta 1 plus theta 2 plus theta 3. Everything is relative to the previous joint. That's just kind of the notation we use in robotics. So forward kinematics is pretty easy. I just take the x-coordinate is the radius times cosine theta, or the net angle. The y-coordinate is radius times sine of the angle, plus wherever it was before. That's where you currently are. So 5 and 6 is write a little MATLAB program to calculate the tip position. So the program might look something like this. I'm going to call it RRR. This is a rotational robot, 3 rotational joints, passing parameter z. I'm going to parse it. What z means is the angle of Q1, Q2, Q3. Again, MATLAB uses radians, so if I tell it it's 41 degrees, I'll convert to radians for the 3 angles. Then calculate where the positions are. The first one has the length of 3. X is cosine theta, y is r sine theta. The second link is where the previous link was, plus r cosine theta, r sine theta. The third link, so on. That's all I really care about. What is x3, y3? So we return x3, y3 and save that. What I can do is you can't run functions, but I can call them. From MATLAB, I can say what is RRR, x, y is RRR of 30 degrees, 40 degrees, 50 degrees. and got to get the notation right. I pass it as a single number, so I'll pass that as a single matrix. So that's where my robot is. The tip position is at 2.78 meters, 4.24 meters. I can pass other things. Let's do 130 degrees, minus 40 degrees, 50 degrees. Oops, off the screen. 80 degrees. That's forward kinematics. You just specify the angles, and that tells you where the tip is. So that's one of the reasons we cover trigonometry, is if you get into robotics, it's all about sines and cosines. The final one is a function in MATLAB called fmin search. This is the inverse problem. To know where the tip position is, what are the joint angles? So to do that, I want to set up a function equals 0. I'm going to calculate the distance from the tip position to the point 2, 0, and instead return that distance. The goal then is to come up with a function equals 0. What angles put you at 2, 0? So what I can do is guess, guess again, guess again. So if I try this now just returns a single number, the error. I'm off by 4.19 meters. I can guess and say, let's try, this goes down a little bit. It's now 2.47 meters. You can keep on guessing, guessing, and guessing again, or let MATLAB guess for you. So here what I'm doing, I'm using the function fmin search. Fmin search finds the minimum of a function, or what angles put me as close as I can to the point 2, 0. When I run it, you can see it guessing, guessing, guessing again. Eventually, once it finds an answer, it'll spit out and says, one answer that put you there. Drum roll, please. Takes a little bit of time to run. Is 61.2 degrees, minus 121 degrees, minus 56 degrees. This is optional. I just plotted where the robot is right here. It's kind of fun to see what's happening, but not necessary for the homework. This is one solution. I've got 3 degrees of freedom and 2 constraints, x and y. What that says is there's an infinite number of solutions. If I give it a different initial condition, I'll get a different answer. So here's another solution. It's going below the screen. But that's homework set number 3 for ECE 111, playing around with sines and cosines, stuff you're going to do when you take trigonometry. Only instead of solving the equations by hand, like you do when you take trigonometry, solve them using MATLAB. If you get stuck, a good place to go is under Homework Sets and Solutions. Here are solutions to the previous semesters. The problems change every semester, but kind of give you an idea. So that should get you started on homework set number 3.